Good evening and welcome to our 8th lecture. Today we'll discuss the Fourier series and Fourier transform for discrete time systems. Previously, we've discussed the transformation of our z-domain function into the frequency response. Here, we'll take a direct step from the time domain to the frequency domain using this Fourier series and Fourier transforms. So we'll start with the Dirichlet conditions, and then we'll end with discrete time operations and solving discrete time systems in the frequency domain. As I've mentioned, the frequency response of discrete time systems can be directly obtained from the Fourier series and Fourier transforms of the signals. Now, Fourier series are for periodic signals, while the Fourier transform is for aperiodic signals. Similar to the Laplace transform, we should have specific conditions for the existence of our series and transforms, which are known as Dirichlet conditions. Here are the three conditions. First, the discrete time signal should be absolutely summable. This is a strict requirement since in order to get to our omega domain, we should perform summation over our time domain. Next, there should be finite discontinuities within the signal duration. Now, this is more applicable to continuous time signals, as discrete time signals are all discontinuous. Third is that there should be finite extrema, a minimum and a maximum, within the signal period or the signal duration. So periodic signals can be expressed as a combination of harmonically related complex exponentials. And this is shown by the following formula. Now, this equation is also known as the synthesis equation or the inverse transform of our Fourier series. So here we have the summation of our C sub case or our frequency domain coefficients multiplied to e to the jk omega naught n, and the sum of that will be our signal in the time domain, which is our x of n. Now, in order to get the coefficients, this C sub case, we need to perform the analysis equation, which is defined as follows. So we need to get the period of our function, which is denoted by n, and then we multiply 1 over n to the summation of our signal multiplied to the e to the minus jk omega naught n. Another form is that we can represent this omega naught as 2 pi over big N, where the big N is our period. Now let's try to get the Fourier series of a sinusoidal function sine omega naught n. The first step is to express this function using Euler's formula. Here we'll have two complex exponentials at 2 pi over n and negative 2 pi over n. And we'll see that it already has the coefficients 1 over 2j. So here, there's no need to use the analysis equation since this is already in the form of our synthesis equation. So this 2 pi over n here occurs at k equals 1, and the magnitude is 1 over 2j. And the other frequency is at n minus 1, so the coefficient is negative 1 over 2j. Here we have a periodic pulse train which repeats every 10 samples. So here we need to use the analysis equation of C sub k. So our n equals 10. We have 1 over 10 times the summation of our signal over one period. So we have a choice to sum from 0 to 10 or from negative 5 to 4 as shown here. And then multiply our signal x of n to e to the minus jk 2 pi over 10 times n. So getting this summation is easier since we will just have these straight ones from n equals negative 2 until n equals 2. And here we'll have a function of our C sub k. Now we can further reduce this expression into a closed form expression by letting n equals m minus 2. And then we'll rearrange the terms, so we'll get a function that is purely expressed in terms of k. So if we have this C sub k formula, we just need to evaluate it at different k in order to get the magnitude response. Now, some notes on the Fourier series. Based from our two examples, we'll see that our C sub k's are periodic with respect to n. And here, what will happen if we increase our n? If we increase the n, our spacing between the C sub k's will be smaller. Now, if n becomes infinity, then our discrete time signal becomes aperiodic, and then the spacing becomes so small that the frequency domain becomes continuous, as shown here. So this is where we have our Fourier transform. Now, for the analysis equation, we just need to sum from negative infinity to infinity of the x of n multiplied to e to the minus j omega n. Now, since our signal is still discrete, our spectrum will still be periodic. However, the spectrum will now be continuous. And comparing it to C sub k, we'll just negate this scaling factor 1 over n, and our 2 pi k over n is now an omega. For our synthesis equation, we just need to integrate our continuous function in omega over a single period. Let's take a look at an example. Here we have an aperiodic finite signal defined by 3 impulse functions. If we apply the Fourier transform, we'll get 3 terms, and we can expand these terms from -1 until n equals 1. And here we'll have our continuous function in omega. And here we can verify that this particular function is a low-pass filter. And shown below is the phase response. Now, some properties of our discrete time Fourier transform. We also have the linearity, similar to the Z transform. We also have the time shifting, frequency shifting, modulation, folding, and conjugation, all very similar to our Z transform, with just Z equal to e to the j omega. And then we also have some modifications for the differentiation. The convolution is still the same. And here you also have windowing and Parseval's theorem, which is very useful in filter design and getting the energies of our signals in the frequency domain. Here is an illustration of frequency shifting. So here, if we multiply our signal x of n with an exponential signal, we'll see that our signal x of n with this particular frequency response will just be shifted by omega c from this complex exponential. So our frequency response will be shifted to the right by omega c. For modulation, if we multiply our signal with the cosine, since the cosine is 2 exponential functions, we'll actually replicate the signal into 2 symmetric functions, one on the left and one on the right, with respect to omega c. Here, if we have 2 discrete time signals which are being convolved, it's similar to multiplying the magnitude responses in the frequency domain. Some notes on the discrete time Fourier series and Fourier transform. All the discrete time signals are periodic in the frequency domain, and it is the duality of the time and the frequency. So if we also have periodic discrete time signals, we have discrete and periodic frequency domain signals. If we have aperiodic discrete time signals, the aperiodic will translate to a continuous spectrum, which are also periodic. And the Fourier transform of the impulse response is also the frequency response. So instead of going into the Z domain and letting Z equals e to the j omega, we can directly get the frequency response by applying the Fourier transform to our impulse response. Lastly, the Fourier transform is also the Z transform evaluated at the unit circle or at r is equal to 1. So here is the duality with respect to the symmetry. So if we have a real and odd signal, we'll get an imaginary and odd signal in the frequency domain. If we have a real and even signal, we'll get a real and even signal in the frequency domain, and so on and so forth. Here we're asked to determine the response when this is our input and this is our system impulse response. What we'll do here is that we'll get the Fourier transform for each of these signals. And here we'll notice that our x of n occurs at only a single frequency. So here we can just get the response by amplitude scaling and phase shifting our input function. In order to do that, we need to get the Fourier transform of our h of n and evaluate the Fourier transform at this particular omega. So after getting our h of omega, we need to evaluate it at omega equals 0.5 pi, and then we'll get the magnitude and the phase shift that will modify our input ae to the 0.5 j pi n. So shown here is the output response, which is just an amplitude scaled and phase shifted version of our input. In summary, the Fourier series and Fourier transform allows us to transform signals into the frequency domain. And the frequency response can be derived by getting the Fourier transform of our impulse response. Lastly, it's just easy to get the sinusoidal steady-state responses since we just need to evaluate our h of omega at the input frequency. For further reading, I'd recommend these chapters from our references. And that's it. Thanks for listening.